Hi, and welcome to another lecture in this series. In this lecture, we will talk about how to improve your deep neural network. But before we jump into that, let's talk about some practical aspects of deep neural networks, starting with the training, dev, and test set. So what do these terms mean? A training set is the data which we use to train our model on. The dev set is the data which we use to check how well our model is performing against the model created with the training data. The test set is after we have trained the final model, we evaluate it using the test set. Now, many people mix the test set with the dev set, where instead of using dev set, they just say test set. The test set should be a set of data that gives you an unbiased estimate of how well your algorithm performs. So therefore, this is the type of data that you don't use to check on with your train set model. So what should be the length of these training models? How much data should be used for training? How much data should we use for the dev set, and how much data you should use for the test set? Now, if we look at these three lines to the right, we can roughly see that if you have the training set should be 60% of your data, while the dev and test set is divided to 20/20. I mentioned briefly previously people mixing up dev and test set, but in that case, if you don't want to have a dev set, then people jump straight into the test set and you use it to check how well the model is performing. Well, in reality, this should be referred to as the dev set. So if you have less than 1 million points, then these two distributions are completely fine. But once you go into the 10 million and 20 million and 30 million range and the big data realm, then it's recommended to have a 98% in the training set and 1% on your dev set and 1% on your test set, or even sometimes 99% on your training set in the big data realm. So another important point to talk about is that you should be using the similar data distribution across your training, dev, and test set. So for example, don't build your training set model from images you download online, while your dev set and test set are actually images gathered by the users in real life. So it's very important to distribute the amount of data and the type of data across equally. So if you have 50, let's say you got 100 image, so let's say 50 of those are going to be from the internet and 50 from those are going to be real life, and that should be equally represented in your dev set, so you get a realistic percentage or a realistic view on how well your model will perform. So once you have the train, dev, and test set divided, what do you do next? You want to know how well your model will perform, and this is where the next two terms come in, which is bias and variance. If your model underfits your training data, then you have high bias. On the other hand, if the model fits the training data perfectly, then you have high variance, and that is basically overfitting. The right model is the one that is between these two extremes. We want the model to just be right. We want it to have low bias and low variance. A high of any of these two terms will mean that the model is not performing well. So let's take a look at this table here. If the dev set error is much more than the train set error, then your model has high variance. It's overfitting, meaning that the error is only 1%, it perfectly fits your training set, but boom, it goes out to the dev set, and there it is, 11%. So you really have high variance here. When both the train and dev set are high, then the model is underfitting and has high bias. It doesn't understand what is happening here. It doesn't see your data. If the train set error is high and the dev set error is even higher, then your model has both high bias and high variance, and this is a really, really bad scenario here. However, when both the train and dev errors are small, then the model is reasonable and we can say you have low bias and low variance. So the aim is to always have this low bias and low variance. So what do you do to deal with high bias? Something you can do is you can increase your network size, and you have high bias as shown by the table up here is if you have a high training set error. That means you have high bias, increase your network size, or train your model for a longer time. If you have high variance on the other side, which can be these, well, these three examples really, then you should use regularization, which is down here, or increase the amount of data that's in the model. The next slides will focus on using regularization to deal with high variance, and that is when your data fits your training model perfectly. To deal with high variance, we look into regularization. So how do we deal with this high variance? We can reduce the variance by increasing the amount of data. But is this really a feasible option every time? Perhaps there is no other data available, and if there is data available, it might be too expensive to collect. This is quite a common problem, and that's why the concept of regularization plays an important role in preventing overfitting. The primary reason overfitting happens is because the model learns even the tiniest detail presented by the data. So after learning all the possibilities the pattern can find, the model tends to perform extremely well on the training set, but fails to produce good results on the dev set and the test set. It falls apart when it's applied on data it has not seen before. One way to prevent overfitting is to reduce the complexity of the model, and this is what regularization does. It reduces the complexity of the model. Now, in this lecture, we're going to look into L2 regularization, or weight decay, as it's sometimes referred to. So this is our forward propagation equation that we have seen over the previous lectures and explained it. And with regularization, basically, we add a new term to the right of the cost function here, where W here stands for this. On the backward propagation, we update the equations as follows. So without the regularization, this is how our backpropagation looked like normally, and with regularization, we simply add the lambda term at the end here, and we update our weights using this new lambda over m term. So what is this lambda really doing? If the lambda value is really big, then the decay in the weights during gradient descent update will be more. Hence, the weights of most of the hidden values will be close to zero. So if the value here is too large, then this will consequently reduce the value of the weight. Now, let's understand this concept with another example. Suppose we have a tanh function right here. And if we set the lambda function to be very, very large, the weights of the unit W will be less. Hence, the Z value will be less. So if we look at this tan H function here, all the values will start to lie in this area here instead of the extremes. So if the value is too big, it will be pushed down here, and if the value is on this side, it will be pushed up here. So when the values come in the middle here, this will cause the output of the value to be linear. So the tan H function actually becomes linear. And when a function is linear, it starts to reduce the amount of boundaries and overfitting in your data. So if the weights are too large here, what this model will do is going to turn it linear. And when the model becomes linear, it's basically passing through a normal linear function with no activation. So by reducing this amount of neurons that the data gets weight affected from, then we simply reduce overfitting, since the model doesn't have any patterns to learn from. Regularization introduces linear boundaries, meaning a straight line instead of the overfitting curve. And this is how it really stops the model from overfitting. Now, let us talk about another technique of regularization that is called dropout regularization. If a neural network is overfitting on the training data, and we add a dropout of 0.5 as shown in the image to the right, then the model will randomly remove 50% of the hidden units from each layer, and we finally end up with a much simpler network. This has been proven to reduce overfitting, and we will actually get to code this in the next lecture. So basically, by removing these connections to these neural networks, we can take the model from the right side here to the left side here. So we go from high variance to just right. Since these little neurons here makes the data fit perfectly, Another way to reduce regularization, or sorry, another way to add regularization to your neural network, which then in turn reduces overfitting, is early stopping. And basically, here we see that the training error is continuously decreasing with respect to time. On the other hand, the depth set error is decreasing initially before increasing for a few more iterations. Therefore, we can stop training at the point where the depth set error starts to increase. This is in a nutshell called early stopping, and is a third way of also doing regularization. Now that we spoke about dealing with variance or overfitting, let us talk about how to speed up the training process without compromising on your accuracy. So there are four ways you can speed up your training: by normalizing your input, by vanishing exploding gradients, by way initialization of your deep network, or by gradient checking. Or gradient checking actually slows down your training but guarantees that you have calculated the derivative's accuracy. You have calculated the derivative accurately. So let's start with talking about normalizing inputs. Speeding up the training can be done using normalization. Let's take a look at the left graph here, which shows the input x1 and x2. And now let us look at the normalized form of that graph. What we basically did to move this graph from looking like this to looking like that is we normalized the data, which is basically calculating the mean and subtracting it from the input features, then normalizing the variance. And by doing so, we speed up the algorithm. But some can wonder, why does shifting the data from this here to that speeds up the algorithm? And that is because normalization changes the scale of features from asymmetric to symmetric. So since x1 can be on a scale of 0 to 1 million, and the scale of x2 can be from 0 to 0.001, this causes the data to be presented in an asymmetric shape in a higher dimension. Of course, this is a simplified 2D, but in a higher dimension, these scales makes it hard for the gradient to learn. If we set the learning rate to be 0.001 and your scale here was in the million and your scale here was in the nanos, then we can see that this causes an asymmetric shape, making the algorithm super slow in learning any rates. So therefore, by normalizing it, we have equal scales on all dimensions. So when you move in one step in the x1 side or in the x2 side, it will be equivalent. Now, what the mean and variance do is that it brings the mean of the data to 0. So the mean of this data is 0 and the variance is 1, rather than it being scattered all over the place like that. So this speeds up our training process, or one of the ways to speed up our training process is by normalizing the input. Next, let us talk about vanishing and exploding gradients. While training deep neural networks, sometimes the derivative slopes can become either too big or very small, which makes the training phase quite long. For deeper networks, W will be large. So this value here, if you remember that W gains a derivative slope on every layer. So this will be very apparent in deeper neural networks, that this value here gets eventually very, very large. And if that happens, this is called an exploding gradient. Some people would then initialize W to be very, very small, like 0.00 something. Very small, and as a result the learning rate becomes super slow, and this is known as the vanishing gradient. So how do we deal with this problem? What do we initialize W as in order to prevent the exploding vanishing gradient problem? A paper released in 2015 called Xavier initialization, and one potential solution to deal with this is by random initialization, but not just random initialization, but also adding this part here at the end to the random initialization. And in this way we ensure that we break symmetry and we make sure that different hidden units learn different patterns. So there's huge literature around this paper here on how will this help prevent the exploding and vanishing gradient. And in this way we also can speed up training, since the derivative doesn't get too large or it doesn't get too slow. Finally, let us talk about gradient checking. And as mentioned earlier, this does not speed up the training process, but actually checks the sanity over all the regularization that you've been doing. So basically, it is used to find bugs when you implement the backpropagation. This is the equation for gradient checking, but don't worry about it too much for now. In the coding exercise, we're going to go into much more details on what entails into each of this. But basically, this is d theta approximate and this is d theta. So d theta approximate is calculated by taking all the weights and your biases and putting it in a giant vector and calling it j theta. And then we take this j theta and we add an epsilon, and epsilon is a small value, and subtract it by the j theta with also these small epsilon, and we divide it by 2 times epsilon. And this is how our d theta right here is approximate is calculated, while the d theta takes in the dwl and dbl and puts it also in a giant vector, and it gives you the d theta. Now, if the value or if the outcome of this equation is less than 10 minus 7, so this has to be the other way, sorry, I'll fix it. So if this is 10, if the value is less than 10 to the power of minus 7, then that's good. That means you have no bugs in your backpropagation. If it's around 10 to the power of minus 5, then it's almost acceptable. But if it's bigger than 10 to the power of 3, then I will start to worry. So to summarize, we have looked into a way to split and understand the results of your training, dev, and test set. If you have more than 1 million data, then you start looking into 98% training data and 1%, 1%, or even 0.5, 0.5%. The first way to deal with overfitting is look into L2 regularization, which is basically looking into the value of the hyperparameter that we can use to tune the dev set. By looking into our lambda function in the L2 regularization, it makes the decision boundary smoother. If the lambda function in the L2 regularization it is too large, then we can possibly look into over smoothing and even resulting in high bias. So we have to be careful with our lambda function not to be too large in our L2 regularization when we have high variance. L2 regularization basically relies on the assumption that a model with small weight is simpler than a model with large weights. Thus, by penalizing the square values of the weights in the cost function, we reduce all the weights to a smaller value, and as we presented, it then starts to become in the middle of the tan h, which then turns to be a linear function slowly and slowly. So dropout is the second way to reduce overfitting, and dropout is a regularization technique. You use dropout during training, but not during testing. We actually forgot to mention that earlier. And dropout is applied both during the forward and backward propagation, and we will also look into that when we start the coding exercise. Thirdly, to reduce overfitting, we can avoid the exploding or vanishing of the gradient. So it's not really overfitting, but it's speeding up the training process. So to speed up the training process, we look into random initialization, which is the Xavier method, for example. So basically, these two methods here are related. I'm gonna fix this 2 typos here. So I just quickly fixed that. So basically, to speed up the training, we look into the weight initialization with Xavier, and that ensures that we break symmetry and prevents the vanishing exploding gradient. Another way to speed up your training is by looking into the normalizing the input, making sure that the mean is 0 and the variance is 1. Thus, we have the same scale for all your inputs and higher dimension, making it easier to converge to the global minima. Finally, we also presented a method on gradient checking to check your backpropagation calculation. If you have any questions, let me know. Otherwise, check out the coding for all these next.